we've seen now how to, over a rectangular region R, say AB cross CD, we've seen now how to define the integral over this region R. To calculate the volume, this gave us the volume above the region R and under our function, like under the surface, right? And so in general, it's good to learn how to find the integral over an arbitrary region. And so what we want to define now is, imagine within some rectangular region, we have an arbitrary region in here, D, where the boundary could be pretty complicated, right? And now what we want to define is the integral over the region D here. And how can we do this? Well, actually, we don't need to kind of reformulate a definition for the integral like we did in the previous video, because we can be a little bit clever here. So if we want an integral just over the region D, let's be pretty clever. Let's define a new function, g of xy, to be f of xy when, so let me get some more room here. Right, let's define g of xy to be f of xy when x and y is in this region D, and 0 when x and y is not in this region D, but x and y are still in R, right? And so basically what we're saying is this new function g takes a value identical to f over this region D, and then over the region R set minus D in red here, right? That's what this region is. It's x is in R, but x is not in D. This is also, you could also write this as xy belongs to R without D, right? And so when it's in this subset of the rectangular region here, then we'll say that it takes a value of 0. Well, then in terms of the integrals, we have that the integral over the region R of this function g of xy, right? Because this function is defined over the entire rectangular region. Well, because everything outside of this region D is 0, well, this is going to be the same as the integral of the region D, or the integral of f over the region D. And so because of this, we don't need to try to come up with like a new limit definition for integrals over a rectangular region, or over an arbitrary, like over a general region, right? All we have to do is consider just the standard double integral like we were doing in the last video, but now we can look at arbitrary regions. And there's two main types of regions we can look at, right? And so there's a type 1 region. A type 1 region is a region where D is bounded by constant lines x equals a and x equals b, and two continuous functions, say y equals g1 of x and y equals g2 of x, right? These functions, or this domain here, could be extremely complicated, like the boundary of this domain can be arbitrarily complicated. And so because of that, we want to think of the boundary as a collection of smooth curves, right? And so the first type is to think of this type of region where you have, like, say, x equals a and x equals b. We have vertical lines here, and then we're also bounded between like two smooth functions, like y equals g1 of x, and then maybe some other smooth function, y equals g2 of x. And here, this region bounded by these four smooth curves, this is like the region D that we'll say is of type 1, right? And type 1 basically means that the x bounds are constant and the y bounds are functions of x. Okay, and so another example is like they don't, like the functions can intersect. So like say they intersect at a and b, and here we're technically not bounded by like vertical lines, we're just bounded by points, right? But this is still a region of type 1 because in the y bounds, the bounds are both functions of x, right? And so this would be like y1 of x, or how about g1 of x and g2 of x, something like this. And then the next type of region is a type 2 region. And a type 2 region is similar, but now it's bounds by like y equals c and y equals d. So bounded by horizontal lines, y equals c and y equals d, and smooth curves like x equals h1 of y and x equals h2 of y. And so you could have something here now where you're bounded by horizontal lines, say this is y equals c and y equals d, and then you have some like smooth curves here, say something like this, where this would be x equals h1 of y, and this would be x equals h2 of y. And then your region bounded by these four continuous curves is, this is our region D, and this is what we call a region of type 2. And so it's a region of type 2 if it's bounded by constant y values and then functions for x values. And then it's a region of type 1 if it's bounded by constant x values and functions for y values. Okay, and again, like just for example here, you could have something where the curves intersect at like y equals c and y equals d, but then you're still bounded by two functions of y, right? Like h1 and h2. And so these are the main types of regions. And I want to make a remark here is that sometimes you can express a region in as type 1 or type 2, and depending on the region itself and what you're integrating, it could result in an easier integral expressing it as either a type 1 or a type 2. So here's a quick remark. My remark is that some regions can be expressed as both. Okay, so let's look at an example. Let's look at a region bounded by y equals root x and y equals x cubed. So this is a region of type 1 for now, right? And so we have to look at their intersection points and see that this is between 0 and 1. And so this region D here, we can express this as a type 1 region as points x, y, in R2 such that, well, and then x is between 0 and 1, and y is between x cubed and root x, right? And so this is our domain in here, this region D. Now, how could we express this as a type 2 region, right? Well, let's look. Let me redraw. We have y equals x cubed, and then y equals root x. Well, if we just simply write the curves as functions of the other variable, well, so for the bottom one, then we would get x equals the cube root of y, and then for the top one, we would get x equals y squared. You can see we just solve for the other variables, right? Like here, this is a type 1 region, and so our y bounds are functions and our x bounds are constant. But for a type 2 region, we want that our y bounds are constant and that our x bounds are functions, right? And so we can write our x bounds in terms of the functions that used to be the y bounds, right? And now we can see, well, what's our lower bound and what's our upper bound, right? If you pick a point here and you draw a line, which curve do we pass first? Like if you draw a line like perpendicular to the y-axis, right? Which one do we pass first? Well, we first pass the line x equals y squared. And so we want y to be greater than or equal to, we want x to be greater than or equal to y squared. And we want it to be, we go to the next point, we want it to be less than the cubed root of y. And also, then we want to see how our y bounds go. Well, our y bounds start at 0 still because the curves intersect at y equals 0, and then the curves also intersect at y equals 1. And so the bounds for y become 0 to 1. And now as a type 2 region, we can express D as the set of points x, y in R2 such that y is between 0 and 1, and then x is between y squared and the cube root of y. And now we've expressed this region as a type 2 region instead of a type 1 region. And we'll see in a bit the reason for this is because if we were to integrate some function over this region, these are the bounds. And so now we're going to have functions in the bounds even, right? And so when we integrate and plug in the bounds, we're going to get functions. And because of that, it can become extremely difficult based on what functions are in your bounds. And so if it's easier to integrate a given function with respect to a certain set of bounds, well, then you should convert your region into being expressed that way and then integrate. And so we'll see examples of that later. But for now, it's nice to get comfortable with going back and forth between type 1 and type 2 regions before we even start talking about integration, because this is just set manipulation, basically, right? This is just algebraically expressing the same curves in terms of different variables. And so now let's discuss Fubini's theorem for integrals over these general types of regions. So here, this is a stronger version of Fubini's theorem. And so for D, a region of type 1, we can write that the double integral over this region of f dA is equal to, well, it's going to be the double integral over our region D of f of xy, and we know what dA is, but we need to write dA in a specific way, and I'm going to write dy dx first. Fubini's theorem tells us we can flip, right, interchangeably, but when we have when we have functions in the bounds, there's a lot more work that comes with flipping the integral. You can flip the integral for a general region, but you have to rewrite the bounds just like we did here, as when we wrote them from y bounds to x bounds, right? And so what Fubini's theorem says here is this is the iterated integral. This is y equals, so our y bounds are functions, right? G1 of x to G2 of x. And then our x bounds are numbers, so a to b, f of xy, dy, dx. Now, if we were to flip this, right, you're only allowed to flip this if you also rewrite the bounds so that y becomes constant and x becomes functions. Because if you integrate x first here and leave y, like G1 of x and G2 of x, well, then you've already integrated with respect to x, but there's still x's involved in this integral, which means your integral didn't pick up everything that it needs to know. And so because of that, you have to integrate with respect to y first to get all your information from the x variable out of the bounds and into the function. And once you do that, then you have all of your information about the x variable actually as part of the integrand, so that when you integrate with respect to x, then you'll just get some number, which is giving you volume, right? What is this doing? These integrals are giving us volume. We have like x, y, z here. So we have some region D. Over this region D, we have our surface. Does something like this. And we're looking at the volume that's bounded above our, above the region D and below the surface, right? And so for Fubini's theorem, and the stronger version of Fubini's theorem says for a region of type 1, you need to set up the integral this way, where you start with dy first because your y bounds depend on x, and you can't integrate with respect to x while your y bounds still depend on x. And so for a type 2 region, you get something similar, right? You get that we have the integral d f of x y dA is equal to the double integral over the region D of f of x y dx dy this time, because now the x bounds depend on y. And so this is the integral from x equals h1 of y to h2 of y, and then y is bounded from c to d of f of xy dx dy, right? And again, here you're integrating with respect to x first, and then with respect to y. And if we want to flip the order, we have to do like what we did in this example, where we change the bounds. So if we are integrating over a region of type 1, but we want to flip the order of integration, we must convert to a region of type 2 when we flip the order. So Fubini's theorem still holds and says you can integrate in whatever order you want, but there's a lot more that comes with it, right? You have to switch the bounds as well. Otherwise, the result won't, it'll be a nonsense answer, right? Because you will have integrated with respect to y, but then there are still y's in your answer, which is not what we want. So let's see an example here. Let's evaluate the double integral over the region D of x squared e to the xy dA, where D is the following region. It's points xy in R2 such that x is between 0 and 2, and y is between 1/2 x and 1. Okay, so let's see what this region looks like. And understanding what it looks like geometrically can really help when switching back and forth between regions. So let's see here. We have x is between 0 and 2, okay? And then we have y is between 1/2 x and 1. So 1/2 x is a line with y-intercept origin, slope 1/2. And so when we'll go 2 units over and 1 unit up, because it's rise over run, right? So this is our bottom bound. This is like g1 of x equals 1/2 x. And then our top bound is the line y equals 1, which is constant. And this is still a function, right? This is still g2 of x equals 1. And then we're bounded by 0 and 2. And so we know our region D is this right triangle here. So this is the region D that we're looking at. And we can see that we have constant x bounds and the y bounds are functions. So, or at least one of them is, right? Which tells us that this is a region of type 1. And so when we set up the integral d x squared e to the xy dA, we can express this as, because y has functions in the bounds, we need to integrate with respect to it first. So this is from y equals 1/2 x to 1, and then x equals 0 to 2 of x squared e to the xy dy dx. Okay, and now let's integrate. After we have the integral set up, we need to actually evaluate said integral. And so if we integrate this with respect to y, looks like we're going to get x squared over x e to the xy from 1, or from 1/2 x to 1, right? dx, which is the integral from x equals 0 to 2. And so where did this over x come from, right? It's because when we're taking the antiderivative with respect to y, everywhere you see an x, you treat x as a constant, right? And so if we treat x as a constant, well, then the x squared out front is just along for the ride. And then the x here multiplied in front of the y, well, you remember that the integral of e to the ax dx is equal to 1 over a e to the ax, like plus c if it's indefinite, right? And so because of that, now we're looking at, let's say this was a y dy. Well, now we just can use x like we used a over here, which means we end up dividing by an x, right? And so what we get then is, well, we have an x here, and then where we see a y, we plug in 1 first, so e to the x minus, and then we plug in 1/2 x for y, and that's going to be minus 1/2 x squared dx. Okay, and so what is our integration now? It's the integral from x equals 0 to 2 of x e to the x minus x e to the 1/2 x squared dx. Okay, and from here, the rest of the problem is single variable calculus, right? So I'll leave the rest for you guys to finish the problem up. This part requires one step of integration by parts. You let u be x and dv be e to the x dx. So du is dx and v is e to the x. And then this integral, you use u sub, where u is 1/2 x squared, so du is x dx. And you can use these here to finish up this integral, and you can verify that you get 2. Okay, and so since the sake of this lecture is more about setting up the double integrals and doing multivariable integration, once you get to the single variable integration stuff, this is all Calc 1, Calc 2, which I'm pretty confident you guys are good with by now. So I would like to do, now I want to give a theorem here. So theorem, let's suppose D can be expressed as the union of two smaller regions where D1 and D2 don't overlap except at the boundary. So what do I mean here is, like, if we have some region D, and maybe it's actually composed of two regions, D1, D2 here. And so we write that this is, if you haven't seen this symbol, this cup means union, right? And it's basically set addition. It means you take this set plus this set. So here, if you have something like this, then the double integral over d of a function is the same as the double integral over d1 of this function plus the double integral over d2 of this function. And here's where this theorem serves useful, is when, you know, if you have a region D, well, maybe if you split this region in half somewhere, maybe it's more convenient to solve the integral over D1 as a type 1, and then over D2 as type 2, or vice versa, or something like this. And so this integral, or this theorem, is helpful when your region is complicated and you may need to kind of partition your region and then handle it in pieces, where it's like, okay, well, it's easier to handle this part of the region as type 1 or type 2, and then it's easier to handle this one as type 1 or type 2. So maybe this one's easier to handle as type 2, and maybe this one's easier to handle as type 1 or something. And so we have this theorem that says, well, that's okay, because you can split up the integral over the regions and then just take the sum of the integrals to get the whole thing. And then this way you can handle each of these integrals in the most convenient way possible. And so the last thing I want to talk about before we wrap this video up is switching the order of integration, because I talked about, okay, well, Fubini's theorem tells us it doesn't matter. We can integrate in either order and still get the same answer, and we can. But when it's a general region and functions are involved in the bounds, you have to do some work when switching the order of integration. So let's see an example of this. Okay, so switching order of integration. Let's say we want to solve the double integral. X goes from 0 to root 2. Y goes from 0 to root, or no, to 2 minus x squared of x e to the x squared dy dx. Okay, and so let's look at this region here. So what do we have? We have the function 2 minus x squared, right? This is a parabola that opens downward with a y-intercept of 2. And we're bounded between this and y equals 0. And then we're bounded between x equals 0 and x equals root 2. So this point's root 2 here. And so this is our region here. Okay. And let's say we want to switch the order of integration. So what are our bounds right now? So to switch, right? Let's look at our bounds. Our bounds right now are, well, x goes from 0 to root 2, and y goes from 0 to 2 minus x squared, okay? And we want to switch these, right? And so the one function that we really need to look at is this y equals 2 minus x squared. When y equals 2 minus x squared, well, that's the same as saying x equals root 2 minus y, right? If you solve this for x, you get x equals root 2 minus y. And so now we want to go the other way. We first want to start with our x bounds. And so where does x start? Well, it starts still along the line x equals 0. But where does it end, right? Well, depending on what y value you pick, where you end is going to be different, and it's a function, right? And so the upper bound, we know the upper bound. It's this function we just solved for. And so our new x bounds are x goes from 0 to root 2 minus y. And now what about y, right? Now we need to see our y bounds. Well, our y bounds now are going from 0, they're starting at y equals 0 here. And we've already accounted for this curve here. So we just need to figure out what point this is up here, right? Well, when x equals 0, y equals 2, right? Because we know that y equals 2 minus x squared. So when x equals 0, y equals 2. And so that means our y bounds are 0 to 2. And so the integral of y goes from 0, so what was it? Yeah, y goes from 0 to 2 minus x squared, and then x goes from 0 to root 2 of x e to the x squared dy dx has now become, by switching order, and we can do this due to Fubini, this integral has now become x goes from 0 to root 2 minus y, and then y goes from 0 to 2 of x e to the x squared dx dy. And now switching has made this easier because this is just a u sub problem, right? Here you can finish this up just with u sub, right? If we let, so maybe I won't finish this the entire way, but I'll at least go through the first integral, right? We can let u be x squared, and so du is 2x dx, which means this is the integral y goes from 0 to 2 of the integral, and I'm going to leave my x bounds here. So x goes from 0 to 2 minus y, and it looks like from our u sub, we're going to get e to the u, and then x dx is du over 2. And so we're going to get 1/2 e to the u du dy, right? And so the reason I'm leaving the x bounds, although at the moment that looks incorrect, is because now when I integrate, I get 1/2 e to the u from 2 minus, or root 2 minus y to 0 dy. Well, before I plug this back in, these are x bounds, right? So I need to resubstitute u. So this is e to the x squared, right? Because u was x squared. So this is e to the x squared from root 2 minus y to 0 dy. And so this integral becomes from y equals 0 to 2. Well, I can pull the 1/2 all the way out front even. And then it looks like I'm going to have e to the 2 minus y, because when I square 2 minus y, root 2 minus y, the square root and the square cancel. And then I'm going to have minus e to the 0, which is 1 dy. And let's just go ahead and finish this out. So we get 1/2 integral y equals 0 to 2, e to the 2 minus y minus 1 dy. And now this is just single variable integration. Well, I get 1/2 times the integral of e to the 2y is negative e to, or 2 minus y, sorry, is negative e to the 2 minus y minus y from 2 to 0. So I get 1/2, and then I get e to the negative 0 minus 2 minus negative e to the 2 minus 0, which is 1/2. And then it looks like I'm going to have negative 1 minus 2 minus, or plus e squared, which is 1/2 e squared minus 3. And so this was my integral, which came from, remember, the important thing here was the switch, was using, when using Fubini's theorem over a general region, I have to play this game with the bounds so that I can switch the order correctly, right? And then once I do that, then this just became a u sub problem, right? Instead of, had I integrated with respect to y first, then I would have had this stuff, but now times 2 minus x squared. So let's see what would have happened. What if I didn't switch? So what if we didn't switch? What if we had done the integral from x equals 0 to root 2, y equals 0 to, what was it? It was 2 minus x squared. And then x e to the x squared dy dx. Let's integrate this with respect to y. Well, if we integrate this with respect to y, all of that's just constant. And so what we're going to get is x y e to the x squared from 2 minus x squared to 0 dx. Well, this is then the integral from x equals 0 to root 2 of x times 2 minus x squared e to the x squared dx. And now what you have is, you know, if you were to distribute this, well, then you'd have a u sub integral, and then you would have a horrible integral, right? X squared e to the x squared. This requires integration by parts. And so you can see the integration itself was much worse off if we didn't switch. And this is why switching can be important. When we switched here, what we did was, instead of passing the work to difficult integration techniques, we passed the work to a lot simpler manipulation of the boundary of a set, right? We're just rewriting how we express the boundary of a set versus trying to juggle a bunch of complicated integration techniques. All right, and there are two more definitions that I would like to give, and then from here we will switch to double integrals in polar coordinates, because sometimes the regions are very polar in nature, right? Meaning they're very easy to represent or understand in polar coordinates, whereas they're not so easy in standard Cartesian coordinates. So after this, we will take a look at double integrals and polar coordinates. But first, I want to define the area of region D is, we say, the area of D, and it's simply the integral of the constant function 1 dA, which is, if you'd like, sometimes you'll just see this as integral d dA. This gives you the area of your region. And then we can use this area of a region to calculate the average value of f of xy over d is, and we write f average, and it's 1 over the area times the double integral over the region D of your function. So this gives us a way of calculating area of a given region and calculating an average value of a function over a given region. And so, like, why you want to know about average values? Well, there's immediately a lot of applications in statistics. And of course, area of a region is always important in many applications in physics, engineering, et cetera, et cetera. And so this concludes our discussion of double integrals in Cartesian coordinates, right? First over rectangular regions and now over general regions. And where we'll go from here is double integrals in polar coordinates.